temperature Ti everywhere inside the body. So it's uniform and it's a lumped system. So all the temperatures on the inside is the same. It has a certain surface area, AS, and on the outside we've got the heat transfer coefficient and T infinite, which is the temperature of the environment. And in this case I'm going to assume that the environment temperature is larger than the initial temperature, which means that the heat transfer will be from the outside to the inside. It can of course be the opposite, it doesn't matter. So the heat transfer rate going into this body can be written in terms of Fourier's law, which you've done with the previous module. It is equal to the heat transfer coefficient multiplied by the surface area multiplied by the temperature difference, which is T infinite, minus the temperature that varies as a function of time. What we're going to do is we're going to take an energy balance by saying the heat transfer rate into the body during a period dt is going to be the same as the increase in energy of the body during dt. The heat transfer rate going into the body over a period dt is equal to the increase in energy dt. If you find it difficult in many cases to work with heat transfer rate, think of it as a mass flow rate. So the mass flow rate going into the tank would be equal to the increase in mass of the tank if nothing goes out. Okay. Let's write that in terms of the equations. It's the heat transfer coefficient multiplied by the surface area multiplied by Ts minus the temperature T over the time period dt is equal to the mass Cp dt. Now the mass, if we look at these two terms, that one and that one, the mass is equal to the density multiplied by the volume, and dt we can write as d of t minus t infinite. Why can we do that? Because this is a constant. And if we do the differentiation of the constant, it's going to disappear. If we substitute this into those two terms, then we can write the equation as the heat transfer coefficient multiplied by the surface area multiplied by Ts minus the temperature dt is equal to rho multiplied by the volume Cpd T minus T infinite. You happy with that? Okay, so what we're now going to do is we're going to get all the temperatures on one side of the equation and the rest on the other side. So we can write it as the heat transfer coefficient multiplied by the surface area divided by rho, the volume phi, Cp, dt is equal to t minus T infinite divided by T infinite minus the temperature. Okay. Now it's almost in the form that we would like to have it so that we can integrate it. It almost looks like dx divided by x if we just change these two around. Okay. Which means that we have to put a negative sign on that side, and then we can write it as t minus T infinite divided by T minus T infinite is equal to minus the transfer coefficient multiplied by the surface rho v Cp dt. You happy with that? If we now do the integration, then we have to integrate that, and if we assume that all this is constant, we can say that when time is equal to 0, then this temperature is equal to Ti. Okay? And at time T, then that temperature is going to be the temperature at T. If you do the integration, you all know how to do it. It's just a simple Lin term. Clean it up and make it neat. Then you're going to end up with the equation, the Lin of the temperature minus T infinite divided by Ti minus T infinite is equal to minus the transfer coefficient multiplied by the surface area rho v Cp multiplied by T. We would like to get rid of the Lin term, therefore we can say the temperature at any time T minus that of the environment divided by the initial temperature minus the temperature of the environment is equal to E to the minus Bt, where B is equal to the heat transfer coefficient multiplied by the surface area divided by rho, the volume Cp, and B doesn't have a physical meaning, but its unit is per second. Thus, if we now look at the solution of temperature as a function of time, then we will always have the solution between Ti and T infinite. And let's suppose T infinite is now larger than Ti, then the solutions, let me just write the Ti there because it's going to be in the way, Ti. That is the solution for a specific value B1. So the temperature is going to do something like that. And as the time goes larger and larger, it will tend towards the temperature on the outside. Okay. If we make B larger, then it's going to do something like that, something like that. So it means that the solution, as B increases, with quicker goes to T infinite. Okay, now, if we are now critical about it, we will say, well, that's now great. I've got this fancy equation that I can now use to solve the temperature inside the body as a function of time. But let's go back to this. And that is about the assumption of a lump system. When would I know I can use the lump system approach? When will it be valid or not? And that is one of the biggest challenges in this chapter for most students, figuring this out. Because in a test and an exam, I'm just going to give you a body, and you will have to choose which approach to follow. The lump system approach is most probably going to be 10 times or 100 times more simple than that of the other solutions. So it's quite a relief if you can use the lump system one, and it's much easier to solve. But it is not so easy to figure out when you can use it. And that is what I'm going to discuss with you now. So the criteria in terms of when is it a lump system approach, or when can we use a lump system approach? Well, before we answer that, one of the things that is being used is the characteristic length. The characteristic length. And the characteristic length is LC, C for characteristic, is then equal to the volume divided by the surface area. Now this characteristic length definition is for lumped only. Of all the other bodies that we are going to do in this chapter, you have to be careful. In most other cases, you have to calculate or determine the characteristic length in a different way. So reserve this definition only for the lump system approach. We need to do that, and then we are going to get a number which is called the Biot number. The Biot number. And the Biot number, we are not going to derive it, but it's very easy to derive, and we are going to do it later on, is equal to the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity K. So that's a mathematical definition, but what does it really mean? What it means is it is the convection, the ratio of the convection at the surface to the conduction within the body. The heat transfer convection at the surface, the convection at the surface divided by the conduction within the body. And in terms of resistances, it is the internal resistance divided by the external resistance. So if we have a small Biot number, then we have a small internal resistance. Small internal resistance. So if the Biot number is equal to 0, then it is actually the lump system exactly. The problem is we do not have any real bodies in which the Biot number is 0. Okay? So that's a practical reality. So that is just a mathematical solution. All other bodies have a Biot number larger than 0. And now we have to determine when and we use the lump system, and we make use of the Biot number. And in general, what is being used as a good criteria is to say that is when the Biot number is smaller than 0.1. If the Biot number is smaller than 0.1, then typically we can use the lump system approach. And to get a small Biot number, if we look at this equation, then you will see it is typically when LC is small. When the characteristic length of the body is small, then it will make the Biot number small. The second thing which can be used to before the time figure out if you can use the lump system approach or not is to look at the thermal conductivity. If the thermal conductivity K is high, then normally we've got a very small Biot number. So if we just think of bodies we can consider, then any small ball, a bearing, typically would have a small characteristic length, high thermal conductivity. So a ball bearing would be a good example of a lump system. The woman that wears some jewelry in your ear, that would typically also be a wire or maybe something fancy on, a harp or something like that. It is small, the thermal conductivity would be high. That would be a good approximation for a lump system. A dead body. Okay, if there was a murder or somebody passed away and they have to determine when the murder took place, then they want to determine by measuring the temperature in the liver when the person was murdered. So a human being, in most cases, is not so small, and your thermal conductivity is relatively low, so that would be not a good example of a Biot number smaller than 0, or we can use a lump system approach. But what is more important is that you really understand this ratio of the internal resistance to the external resistance. It's all good and well to use the Biot number, but that is just to quantitatively have a criteria, but you will see in this module you need some deeper insight. And I'm going to explain it to you with the following example. This is the venue in which you are in the moment. Engineering 3, venue 1. Okay. And there are 300 of you in this venue approximately. And that is the, and let's we close 3 of the 4 doors, and there's a fire here in this venue. Okay. And remember, this represents the body. And the body I'm referring to is now this body. Okay. So what happens here on the surface is the convection heat transfer. So that represents you sitting here in the venue, and we've got this fire. And all of you want to move into this body. You want to go outside. Now, if there's one door and all 300 of you would like to get out of this venue as quickly as possible, there's going to be a big resistance. Why is there resistance? Because the resistance is being determined by the dimensions of that door. Okay. So it is going to be very difficult for all of you to get through that door very quickly. But if we open all 3 the other doors, the resistance will decrease, and you can move quicker outside into the other body. The resistance for you to move outside, to go to the outside, is much smaller. You understand? So it's very simple. Let's look at an example. on the one in your textbook. It's not exactly the same. I've changed it. And the example is about a thermocouple junction. The thermocouple junction has a diameter of 1 millimeter. Diameter of 1 millimeter. Okay. The K value of this junction is 35 watts per meter Kelvin. The density rho is equal to 8,500 kilograms per cubic meter. The Cp value is equal to 320 joules per kilogram Kelvin. The heat transfer coefficient is equal to 210 watts per square meter. Either degree Celsius or degree Kelvin, it doesn't matter. And the initial temperature of this thermocouple is, let's suppose it's in the fridge or the freezer, and it's at 0 degrees Celsius. Okay, and it's 0 degrees Celsius everywhere inside this thermocouple junction. So at T equal to 0, if I can draw it larger, doesn't matter where you measure it, the temperature is going to be 0 everywhere. And also here on the surface, temperature is 0 degrees Celsius. Right. Now at T equal to, when the time starts, we take this thermocouple junction and we put it in a stream or an environment where the temperature is now 100 degrees Celsius. Okay, so here it was in an environment where it was 0 degrees Celsius and we had steady state temperatures. So suddenly it is at 100 degrees, so it means that the temperature here on the surface everywhere is 100 degrees. Okay. Now the question is, how long before this thermocouple junction would be at 99 degrees Celsius. Okay. Not 100, but 99. So it is within 1% of the 100 degrees. How long before it reaches 99 degrees Celsius? So if we do it schematically, we would say there's the temperature as a function of time. This is Ti, where it was originally at 0 degrees Celsius. T infinite is 100 degrees Celsius. Okay. At T equals 0, this body was at 0, and then the temperature is going to increase. After a very, very long time, it is going to be about 100 degrees Celsius, but we want to know that is 99 degrees Celsius. We want to know how long is it going to take before the temperature increases to 99 degrees Celsius. Right, the characteristic length is equal to the volume divided by the surface area. Now this thermocouple junction is a sphere. So the volume of a sphere is equal to 1/6 pi multiplied by d to the third divided by the surface area of a sphere, which is pi d squared. So the characteristic length is equal to the diameter divided by 6. The diameter is 0.001 divided by 6 meters. So that is the characteristic length